In this video cast, we'll take a look at another consequence of intermolecular forces known as vapor pressure. If you can imagine this liquid ethanol existing inside of this container right now, where it only exists as liquid ethanol, and there are no vapor molecules of ethanol at all in the container. After a certain amount of time, some of the liquid evaporates from the surface of the liquid. And that's one of the definitions, actually, of evaporation, is that it only occurs at the surface of the liquid. This change of state from liquid to gas is called evaporation, and it only occurs at the surface of the liquid. Once it starts to evaporate, eventually you'll get a bunch of gaseous molecules bouncing around inside of the container. And then after a little while, we are totally filled with lots and lots of vapor particles inside of the container. Eventually, after a while, some of those vapor molecules start to bounce back into the liquid phase. And after a while, we reach what's called an equilibrium, where molecules enter and leave the liquid at the same rate. This gaseous, or these gaseous particles of ethanol that have exited the liquid phase and become a gas exert a certain amount of pressure on the container, or in this case, on this tube filled with either water or mercury. This height that it causes this liquid to move can be measured and is called the pressure of the vapor from the ethanol. Now, to make it sound fancier, we don't say the pressure of the vapor. We just call it the vapor's pressure, or the vapor pressure. It's the pressure of the stuff that's evaporated from a liquid. It's the pressure from the vapor of the liquid that has evaporated. All liquids have a certain amount of vapor pressure. Some of them very, 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 very tiny. Some of them very, 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 very much. Things that at the same temperature that evaporate very quickly are said to have a fairly large vapor pressure. Things that don't evaporate very quickly usually are said to have a fairly low vapor pressure. We're going to take a look at how vapor pressure is used to explain the phase change from liquid to gas, which is known as boiling. Take a look in your packet, and if you don't have it out, please take it out right now, at the note packet, and take a look at this diagram. You'll see right here that as a substance moves, a liquid substance goes from a lower temperature to a higher temperature, more of the particles meet a minimum kinetic energy needed to escape the liquid. And so as you heat a liquid up, in other words, it reaches a higher temperature, more of that substance can evaporate, and therefore at higher temperatures substances have higher vapor pressures because they have more molecules escaping liquid and becoming gas. Once you reach a certain amount where you have all of the particles able to escape, then you reach something called the boiling point. And if you look in your textbook on page 461, and I'll try to put it in front of you here in color, you can see this graph right here illustrates how vapor pressure and temperature are related for four different substances. Vapor pressure is listed on the vertical axis right here, temperature on the horizontal axis. And as we increase the temperature, notice how the vapor pressure also increases for all four of these substances. Once the vapor pressure reaches the pressure of the atmosphere around it, and if you remember from chapter 10, the standard atmospheric pressure is about 760 torr, then we reach what's known as the normal boiling point. The normal boiling point is where a substance throughout the entire liquid changes from the liquid phase to the gaseous phase. This is what differentiates boiling from evaporation as far as a phase change is concerned. Evaporation, remember we said, only occurs at the surface of the liquid, whereas boiling occurs throughout the entire liquid. And we can see here that water, this blue line, has a normal boiling point of 100 degrees Celsius. But if the atmospheric pressure was actually lower, then we would have a meeting of atmospheric pressure and vapor pressure at a lower point, and therefore the boiling point temperature would be depressed. The boiling point temperature would be depressed. This is what happens on top of a mountain where you have lower air pressure, and therefore since you have lower air or atmospheric pressure, the vapor pressure meets that air pressure at a lower temperature, and water can boil at, say, 90 or 95 degrees Celsius, depending on what altitude you're actually at. Take a look at your practice problems sheet, and let's look at sample exercise 11.15. It says, using figure 11.24, estimate the boiling point of diethyl ether under an external pressure of 0.8 atmospheres. So now it wants us to find the boiling point when the pressure is reduced to 0.8 atmospheres and it's not at the normal atmospheric pressure of 760 torr or 1 atmosphere. So we're going to look at this picture right here because this is just a little bit larger version of the diagram, and we'll find ethyl ether on here. Diethyl ether is right here, and you can see at 760 torr right here, the normal boiling point is approximately about 30, maybe 31 degrees, something like that. But now it's telling us, what would the boiling point be if we were at 0.8 atmospheres? Well, since the vapor pressures right here are given in torr, the first thing we'd probably want to do is convert from atmosphere to torr. And we know 1 atmosphere is 760 torr. And so, without getting too particular about the math here, 0.8 times 760 is about 610 torr. So we want to find 610 torr on here because when the vapor pressure equals the atmospheric pressure, we're at the boiling point. So here's about 610. Follow that over. Find the line right here. Drop it down to the temperature. Drop it down to the temperature. And it looks like it crosses maybe a little bit under 30 degrees, maybe like around 29 degrees C or something like that. And so we can see that diethyl ether will actually boil a little bit lower, or its boiling point will be depressed from what it normally is based on the lowering of the atmospheric pressure around it. So, just to summarize once again, vapor pressure. Vapor pressure is the pressure of the evaporated liquid that bounces against or off of other molecules or a container that cause it to have pressure because it's now in the gaseous phase. Some liquids have really low vapor pressure, some have really high. And one way you can tell if something has a higher vapor pressure is if it evaporates quickly. If it evaporates quickly, then of course there's lots more evaporated liquid to cause more pressure. Good luck with your vapor pressure problems.